Hello students. In today's class we will see few points which are very much important to understand with respect to electrostatics and capacitance. We'll start, and these points are stated as points to ponder. Why so? Because these points will make us to think, how these things are happening. What is, like, there is always some or the other forces existing here and there, but we are only considering one force. So what about the other forces in a whole system? When we say that we are working with a system, there are many things which act on this system, not just electric potential or not just the forces due to electric field lines, but there will exist some internuclear forces, there may exist some gravitational forces, they may get deflected due to magnetic field lines, and so many other factors. So why aren't we considering such factors? So to answer these curiosities, they have mentioned these points which we need to understand. In every situation, if we add up all our factors which is affecting it, then it will become a very complicated situation and we will not be able to figure it out. So what we do, at some point we think that let's assume this is happening. Instead of just saying that this is the shape, like we assume a small charge, we assume a small work done, we don't take a whole parallel plate as the full area, we take a small area, small volume. These all considerations and these all supposes and assumes are basically having their own property here. They help us to make problem easy to solve. So let's start with this point number 1, which states that electrostatic deals with the forces between charges at rest. So in the very first class we have defined electrostatics and electrodynamics. Electrodynamics will be reading in the next chapter, that is electric current. So the electric current basically is the flow of electrons. So here what we read is electrodynamics. Dynamics implies something having energy, something in the motion. So when our electrons or when our charges are in motion, at that point whatever studies we are doing are known as electrodynamical studies. But in the chapter number 1, where we have read about the electric forces and electric fields, and chapter number 2, where we have read about the electrostatics and capacitance, all deals with the charges at static position. Okay, charges which do not show motion. But if there is a force on a charge, how can it be at rest? Like, see, if I will push you, will you be able to stay static? No, not possible. You will fall, or just to try balancing yourself, you will hold the wall, the handle or the desk or the chair, whatever is present near you, or maybe the other person standing near you. So in same way, these charges, when force is applied on these charges tend to move, but there is some unspecified factor or unspecified force, we can say anything. So we can actually say factor when we are talking about anything, but if we are talking about only the force, we need to say unspecified force, which we are not taking into the consideration. So these unspecified forces help this charge to stay static when external force is applied to this charge. The same situation, I am pushing you and you are holding a wall, so you are not falling back. But if there is a force on a charge, how can it be at rest? Thus, when we are talking of electrostatic force between the charges, it should be understood that each charge is being kept at rest by some unspecified force that opposes the net Coulomb force on the charge. So this actually opposes the net charge and helps our charge to be static. Point number 2, a capacitor is so configured that it confines electric field lines within a small region of space. Thus, even though field may have considerable strength, the potential difference between the two conductors of capacitor is small. So, what they aim at saying is, like in the next class, I will show you how a capacitor and a resistor looks like, what is their size. So, you will understand this very much nicely. Our capacitors are basically only this much. You might have seen dal. The size of arhar dal is equal to the size of 1 microfarad capacitor, and that capacitor have two wires like this. One is connected with the positive end, other is connected with the negative end of the battery. So this is the only size of capacitor which holds too much of energy, have capability to hold much of energy. So this capacitor contains these parallel plates which have very small d. D is very small. In this very small d, these electric field lines are confined. They have electric field lines like this, from positive to negative. And these electric field lines which are stored between these two plates having small distance contain a strong electric field. This electric field over here is strong, very considerable amount. This is not very small electric field. As we can see, the size is small, field lines are small, but no, they have very much power. Like just see, we have kept randomly moving objects in a closed space, and then we started reducing the volume of that space. What will happen at a point? These randomly moving things in that space will put so much force on the system that this system will burst. So one thing you can see is when we are filling a balloon with the air. So after a point, like balloon will go to maximum volume. After a point, what will happen? It will burst. So what is it that in case? Like the air molecules inside this balloon will start showing the molecular fights. They will start banging here and there. So they will contain a lot of kinetic energy. Same happens. These confined electric fields have a lot of strength in them. As these are having a lot of strength, the potential which is needed across these capacitor plate is very small. And if we are applying very small potential across this system is able to hold much of a potential energy. We do not need to give too much of potential for making this device store too much of potential energy. So that is the concept of our parallel plate capacitors. Here, using a small voltage, much of potential energy is stored, and then we are using this energy later on as per to our requirements. Coming to the third point states, electric field is discontinuous across the surface of a spherical charged shell. It is 0 inside and sigma upon epsilon naught into n cap outside. Electric potential is, however, continuous across the surface and equal to q upon 4 pi epsilon naught into r at the surface. So this point is extremely important. Make a star mark. This is most important with respect to what? With respect to your board exams as well as with respect to all your entrance examination. You can say that this is the favorite question for the entrance examination, because much of the time we get confused between the symbol of electric field and voltage. So first thing we will read is that electric field is denoted by E. and electric potential is denoted by V. Now they have their own property inside a conductor, on surface of a conductor and outside a conductor. Properties inside, on surface and outside. Okay, see, we have this conductor and this conductor is having center here O. This conductor will be given some charges from outside. These are external charges. These external charges will not go inside this conductor, because inside the conductor it have its own free charges which are in equilibrium state, and these Q inside will repel the charges, the Q external charges, these charges which are coming from the outside. Inter-atomic interactions or internuclear interactions will not allow this to happen. So these Q external charges will settle on the surface, Due to the internal charges, there will not be any generation of electric field. If internal charges are able to generate any electric field, then the story will be totally different. Mostly internal charges are of no use in the electrostatics. So these external charges produce electric field across the conductor. So when this electric field moves across the conductor, it do not go inside the conductor, because inside the conductor there is no external charge present, and hence electric field inside is 0, whereas electric field on surface is given by the formula surface charge density upon permittivity into n cap. This n cap gives the direction, because electric field is a vector quantity, we are mentioning the n cap. So inside it is 0. So when we have taken a conductor like this, we just mention electric fields outside, because no electric field line exists inside. But in case of potential is work done to bring a charge from infinity to the point P. So a charge, external charge, if we are bringing from here to on the surface, we will have a potential V1. Now from the surface inside this, still we will have a potential V1 only, because this external charge which is coming from the infinity to point on surface or any point inside the surface will have the same potential. We have that charge will be crossing the same thing. When charge is crossing the same thing, work done needed will be same only. So potential, when we try to calculate, it will be same inside as well as on the surface of the conductor. So the potential inside and on the surface is given by inside equals to potential on surface and is given by charge contained by the conductor upon 4 pi epsilon naught into r. R is the radius of the spherical body which is under the consideration of study. Okay, now moving on to the fourth point here. The torque P cross E on a dipole causes it to oscillate about electric field E. Only if there is a dissipative mechanism, the oscillations are damped and the dipole eventually align with E. See, when we are talking about the oscillations, understanding the damped and undamped oscillation is very much important. So what happens over here is, these are electric field lines and this is the dipole in this electric field line having a charge plus Q and having a charge minus Q, and having a length of 2a. Now here one thing which we know is E, other thing is the P. P is the dipole moment, and this dipole moment is written as 2aq. Okay, then from this interaction of electric field and the dipole moment of the dipole, we can find the torque. Torque again is a vector quantity and written as P cross E. P cross E, which is further can be expanded as Pe sine theta. Now here see, follow up the green ink. On this point electric field is coming in this direction, so they will try to fold it in this way, and over here also electric field will try to make it rotate in this direction. So what they are trying to do is they are trying to rotate. So just imagine a point where something is deflecting very fast. Okay, you have a watch, and in that watch the second hand or the minute hand is deflecting very fast, like here and here, then coming back here, then going back here. So they keep on like vibrating like this. So after a point there comes a sudden halt or the stoppage. How that is coming? That is coming due to the damped oscillations. See over here, damped oscillations have a maximum attitude at initial position. Later on with time these start to reduce, and a time comes when their altitude becomes 0. So at this point we will say the oscillation is damped. Same happens with the dipole. This dipole keep on moving here, 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 there, and then in this motion due to the torque this dipole reduces its energy. This dipole reduces its energy. So as it reduces energy, these oscillations made by dipole are damped. These oscillations made by dipole are damped. So a point comes where P is dipole moment is alone E. What does it mean? Angle between E and P becomes 0 degree. E also in this direction and our dipole also in this direction. So in such a situation, this equation of torque, as torque is defined as Pe sine theta, what it becomes? It becomes Pe sine 0 degree. What is sine 0 degree? What is sine 0 degree? It is 0. So anything multiplied by 0 gives you a resultant of 0. So our torque becomes 0 and our dipole becomes stable. Torque comes to be 0 and dipole becomes stable. So here the concept of damped oscillation is used, and damping of oscillation happens when in a proper interval our energy is released out of the system or converted into something else, maybe the work or some other energy. Now see the point number 5 over here. Potential due to a charge Q at its own location is not defined. It is infinite. So this charge is present over here, and due to this charge we do not define the potential. This charge is present out of a system and its potential is defined to be infinite. We say that this charge contains infinite potential because there is no other test charge which we can bring in this system to calculate its potential. So here Basically, once we are bringing a test charge into this system, after bringing test charge, we can define the potential with respect to the test charge, but when it is solely present alone, okay. Coming to the sixth point, in the expression QV at R for potential energy of charge Q, V at R is the potential due to external charges and not the potential due to the charge Q. As seen in above point, this expression will be ill-defined if potential at R includes potential due to a charge Q itself. Now in a system we have this charge Q and this is the external charge we are bringing. This charge was present, and in the fifth point we have seen this charge when present alone have infinite potential. So when we bring this charge will tend to exert some potential to this potential due to external charge in the system. So when we define the potential V at point R is due to the presence of these external charge, but not due to the presence of this initial charge into the system. So this should be made the Q we use is because at this Q, at this point, we are trying to find the potential, but that potential is being generated by this charge. Now point number 17, a cavity inside a conductor is shielded from outside electrical influences. It's worthy noting that electrostatic shielding does not work other way round. That is, if you put charges inside the cavity, the exterior of the conductor is not shielded from the fields by the inner charges. Okay. Now I will explain this. This is quite a important understanding. When we see this, we remember one point, that is electrostatic shielding. This hole is a conductor over here. This is conductor, this is the cavity. This is the cavity, conductor, and we are providing the charges to this conductor, external charges, Q external. Now these charges are started getting accumulated on the surface. These charges will not go inside, and as these charges are on the surface, electric field over here is also zero. Okay, so these charges will not be allowed to move and go to this cavity. So this cavity is charge free. This cavity is charge free, or any animal or human inside this cavity will be protected from the external electrical influences. They will not feel the current. So this procedure is termed as electrostatic shielding. But now I have got one idea. I brought external charges from somewhere and introduced these charges inside the cavity. What I have did this thing. I have brought the charges and put it inside the cavity. Now once I put it inside the cavity, as cavity is not a conductor, cavity is a free space, this cavity will have electric field lines going from here to there. Electric field lines. One thing is this. Now there is external charges on the surface also. and the external charges, and these external charges which are sent inside the cavity will start to come together, and then this conductor will not be any more shielded. This conductor will not stay shielded anymore. So we can conclude that when the cavity is introduced with charges, the concept of electrostatic shielding do not hold anymore. So over here is that if cavity gets charge, conductor do not behave as a shield anymore. And now the second thing which you can say is that if cavity is getting the charge, then the surface of the conductor should be uncharged. So the surface, this surface of conductor should behave as a electrostatic shielding. It doesn't happen so, because from on this surface we have many charges here which are not taken in account but do exist. Because of these charges we will have some electric field on this surface of the charge, and hence there will be flow of the current. There will be something on this charge, there will be electric potential as well as there will be electric field lines present on this surface. So in case cavity is getting charged, there will not be any reverse effect shown. The outer surface of the conductor will not behave as cavity. This is only and only, the statement of electrostatic shielding is only and only true for the inside of a conductor, not for the outside of a conductor. So these are the few points where we have to take care and understand properly, which I have explained you in the well-mannered way. Kindly go through these points. These are very much important with respect to your exam, and these are the concept where many people fail to answer properly. So once you read these 7-8 points and then reread the chapter 2, you will get a clear-cut idea of all the concepts in the chapter. Then it will be extremely easy for you to solve any problem related to these concepts. Hope you got it. We'll meet in the next class. Bye bye. And here we finish up our chapter number 2.